Quantum computation has the capacity, the potential to radically transform various industries. We've heard examples in the press and people talking about the implications for cryptography, for drug discovery, to material science, among many other possibilities. And this can really change the way that we approach and solve a whole range of problems, right? In medicine, for example, quantum computing is poised, and already is, accelerating the discovery of new drugs by simulating molecular interactions with really unprecedented speed and accuracy. In an arena like material science, quantum computing can allow us to rapidly simulate the properties of novel molecular configurations. In cybersecurity, right? Quantum computing is powerful, but it's a kind of double-edged sword, potentially undermining today's encryption protocols, but hopefully also providing new ones that are robust against the very quantum technology used to create them. Quantum computing, it may also hold the key to advancing artificial intelligence, enhancing machine learning algorithms, which we all know are vital to AI systems, and providing more accurate and predictive models of a range of physical systems. Our guest for this conversation is a researcher who has really been in the thick of developing some of these very applications, and in conversation he will tell us about them. So I'm pleased to introduce Brian Babbush, who is Director of Quantum Algorithms and Applications Research at Google. His team is tasked with designing algorithms and developing software to solve problems in areas including chemistry, material science, and machine learning.
Hey, Brian.
Good to see you. Thank you.
Thank you.
So I'd like to gain a sense of where quantum computing is really going to have an impact on the kinds of experiences and things that matter to us in the everyday world. And so I thought we would just sort of jump in on some of the ones that we've probably heard most about, and then maybe give us some insight into the ones that perhaps haven't gotten as much airtime, but are really potentially profoundly important for the future. And of course, I think the one that has gotten the most press is this idea of cryptography, because it affects us. We all go online and buy some junk with our credit card, and have I worried about, typing in the numbers and, the CVV and all this stuff, and you're like, I really hope that this is just between me and Amazon,
It's not something you really think about,
but
it's quite important to the function of the internet in particular.
Now, there is this encryption system. We actually have a quick little explainer of it, because it's a little bit involved. So let me just play it, and then we can talk a little bit about it, unpack it just a minute, and see where quantum computation has an impact on it. So let's take a listen to this.
Today's trustworthy encryption algorithms involve two keys, a publicly available key and a private key that is only known to a trustworthy vendor like your bank. Using the public key, you can open a virtual safe and deposit anything valuable you'd like to transfer to your trusted vendor. Crucially, while the public key can open the virtual safe, once you lock it, the public key can no longer access whatever is inside. Instead, the only key that can then open the safe is the private key held by your trusted vendor. Now, how is this remarkable system of keys set up? It all has to do with prime numbers. Recall that prime numbers are special because they can only be divided by one and themselves. So, in today's cutting-edge encryption, two large prime numbers are chosen, but only their product is made available as part of the public key. The encryption is secure because, given the publicly available product, it is devilishly difficult to figure out the prime factors that made it. And it is only with those prime factors that the safe can then be opened. In fact, for the large numbers used in today's encryption algorithms, it would take even the most powerful classical computers billions of years to find the prime factors. So it is only your trusted vendor who has the prime factors that can open the safe. But here's where quantum computing may render these safes useless. Whereas classical computers search for prime factors one by one, quantum computers can explore a vast number of possibilities simultaneously. And through an ingenious algorithm, the quantum computer can be coaxed to home in on that part of the vast calculation that actually finds the answer.
And it can do this really, really quickly in principle, right?
If you have a large quantum computer, yeah.
And so is this something that we should be concerned with now? Is this on the horizon?
Yeah, it's a good question. So certainly, it's going to require a fairly large quantum computer to break the standards of RSA encryption that are deployed today when you're sending encrypted emails or doing credit card transactions through Amazon. However, there's sort of advice that we should probably start switching over to so-called quantum safe forms of encryption relatively soon. And the reason why is because, in principle, a nefarious agent could start saving encrypted messages now, and you might not want to have them able to read those when we do have large quantum computers.
And that's already, I hear that that's likely already happening, right? So these public parts of the transaction, I put my credit card in here, it's encrypted in this way, it's sent in a manner that can certainly be intercepted en route, say, to Amazon.
Yeah.
Someone stores that on the side. They can't get at it because they don't know how to factor that big composite number, but then they gain that ability in 2 or 3 years, and then they can get all that information.
Yeah, it may be a bit more than 2 or 3 years, but that's exactly right. And you can be sure that even governments, for example, you could imagine our government is probably interested in, let's say, Putin's emails or something like this. And
I mean, more than my credit card.
I mean, possibly.
Wow.
So, those are encrypted, but they could still intercept those communications,
Yeah.
and you're not able to read them until they have a large quantum computer, so that makes them sad. But
Now behind this capacity of quantum computers to factor numbers is the fact that there is this, as I mentioned in the piece, an ingenious algorithm.
that's right.
So it is not obvious that a quantum computer could factor numbers until somebody comes along and is able to write down an algorithm that can somehow blend together the morass of calculations that are happening in parallel and focus in on the one that actually factors the number. And of course, it was Peter Shor who did this, but and I actually wanted to try to describe that algorithm here. I sat down and I spent many hours trying to find a simplified version that I could come up with. I kind of failed to do that. I'm going to therefore ask you if you can explain it.
Yeah, sure, I'll try. So in some sense, the art of quantum algorithms is often to sort of recognize how the problem that you're interested in might be susceptible to a quantum attack by nature of having some sort of quantum-like characteristic or nature in the first place. So for problems like quantum simulation, simulating other quantum systems, this is a non-issue. It's very straightforward how to do that. For something like factoring, it's very non-obvious. And sort of some of the genius of Peter Shor in this case was to realize that one could use some insights from number theory in order to see that the problem of finding prime factors is equivalent to trying to find the period, sort of the pattern with which some mathematical function will repeat itself. But it repeats itself over a very, very, very sort of large range of numbers. And it turns out that this problem, sort of finding periods, it's sort of related to the wave-like nature of, it's sort of like a wave-like property. Waves have periods. And it turns out that there's this thing called the quantum Fourier transform, which is a quantum algorithm that's actually very simple. And what it does is it allows you to determine the period of quantum waves that you give it as input. And so it's possible then to sort of evaluate this function over many, many possible inputs and feed it to the quantum Fourier transform. It helps you figure out this period, and that allows you to factor a big number. And I know that is unfortunately not the most elucidating explanation.
No, I think it's kind of good. I mean, because I think part of the intuition, you want to hang it on where are the quantum waves relevant to factoring big numbers. It doesn't seem to be any connection, but this subtle notion that there is this operation in number theory that naturally, as you try to factor, involves sort of a periodic function, a wave-like function, and then you can at least get a feel for where the connection comes from.
It turns out there are some other forms of cryptography that quantum computers can also efficiently break, although hopefully not all forms. And often cryptography it has the feature that you're sort of looking for some hidden structure in a problem. And there are other examples of problems that are sort of about detecting hidden structure where quantum algorithms seem to be able to do relatively well. And it's sort of because you can, sort of evaluate this, sort of all values of this function or whatever it is at once. And then if there is some structure, unlike in, say, a generic difficult optimization problem, you're sometimes able to use that structure to sort of engineer interference that kind of amplifies that structure in a way that exposes itself.
And I want to get to some of those examples in a moment, but one final question on the cryptography and the factoring. What is the largest composite number that has been factored today with a quantum computer?
Oh, not a large one. So I think it depends a little bit on
it's not like 15 or something, is it?
It depends a little bit on sort of what compilation tricks you allow. There are some that are sort of cheating, but it's something like this. It's something like 15 or 25 or something if you sort of compile it without any tricks. But this is a little bit misleading and not a good benchmark of where quantum computers are, because in some ways the factoring application is one that it's really not the most natural application for quantum computers. You have to do a lot of arithmetic, which is generally not something quantum computers are good at.
Right.
And so you might sort of think the constant factors in the algorithm are very large. So even though the quantum algorithm scales relatively well, you sort of need a pretty big quantum computer to do it at scale at all in the first place. So this is definitely one of the applications that we think is at least 10 years out.
Right. So it's on the horizon. The algorithm exists, but implementing it is a challenge.
That's right. But like I say, this is already reason to think about switching over to quantum-safe forms of encryption. Something Google is very serious about doing a lot of work on.
Well, in fact, I think there's actually, wasn't there some kind of competition that was run to try to people come up with encryption schemes that would be impenetrable to a quantum computer? And a bunch were chosen, but are they, we don't need to go into the details of the protocols there, but are we convinced that we have these kind of algorithms that would be immune?
It's a good question. So all that one can really do is present an algorithm and sort of present it to the community and see if the community can come up with a clever algorithm for breaking it. And so NIST, the National Institutes of Standards and Technology, the people that tell us how long a meter is and all this thing, they've been tasked with figuring out sort of what the standards for post-quantum cryptography will be, and they've had this competition going on for a number of years now, and there's been multiple rounds. These are the sort of the ones that have emerged after round 4. So you started with 50 algorithms, and every round they sort of annihilate, they get rid of some.
I mean, are there people who spend their time trying to break?
Absolutely, they do. And say in round 3, I think there were 15. Google contributed 3. This was round 4.
Do you get a bonus or something from Google if you
get rid of one of the finalist post-quantum encryption algorithms?
Nice.
I think you do get a bonus.
Very nice.
So. The reality is there's not that many people in the world that have real deep knowledge of both cryptography and quantum algorithms. So there's really not that many people that think about how you can break these things with a quantum computer. The ones who do think that in particular these first two, which are lattice-based schemes, they look relatively secure. We even have sort of Chrome browser extensions now that implement these.
Oh, really?
But as recently as last month, there was quite a scare in the community where a reputable cryptographer in the community put out a paper claiming to have broken the crypto system behind those first two. Most people I knew that worked on this were immediately suspicious, but had to take it seriously. And after 3 or 4 weeks, indeed, the community found an error. But
Wow.
it's just a reminder that
So it's on
we need
it
to
could
take
be
this
on a knife
seriously.
edge in a sense for that kind of security. Well, look, I mean that is potentially scary, but let's turn now to some other
of the good
interesting applications
Yeah.
of which you know quite a lot. So perhaps the most natural use of quantum computers is to simulate quantum systems.
Definitely.
After all, that's a resonance immediately between these two things. So what have people done in this domain, and where do we think that might be going?
Yeah, so it was the original motivation for building quantum computers. Richard Feynman said, nature isn't classical, damn it, and if you want to simulate nature, you'd better use a quantum computer, essentially. And he said this because physicists had noticed for many years that if you try to use classical computers to simulate quantum systems, the computational effort required to do so appeared to grow exponentially in the size of the quantum system. For example, how many electrons are you simulating in a molecule, or something like this. And as far back as 25 years ago now, we've had quantum algorithms, actually even longer than that, which are universal. They can simulate any quantum dynamics. So since then, there's been a lot of effort in sort of specializing those algorithms to simulate various specific systems you might care about in chemistry, condensed matter physics, high energy physics.
Is this a reasonable collection of places where people have applied these ideas? And there are a bunch of them. I think you have knowledge more or less of all of these. Can you just take us through some of them and give us a feel for what has been achieved?
Yeah, definitely. This is sort of thinking about technologies that would be very helpful for the world, which there's sort of some quantum simulation problem that we know we could solve on a quantum computer that would be very helpful for developing that technology. So, for example, exactly simulating chemical reactions or exactly simulating the properties of a material, like its conductivity or potential or something like this, just from first principles, is something that you can't do. You can't do without approximations in an efficient way using classical computers, but you can do with a quantum computer. And all of these applications, for example, simulating battery cathodes, that's a project that the Google team collaborated with BASF, one of the world's largest chemical companies, on trying to simulate alternatives to battery cathodes that didn't involve cobalt, which is something that's difficult to mine ethically. It's very expensive, and you want to have batteries that don't contain that. And indeed, this is something that with a fault-tolerant quantum computer would be quite a good target. You could imagine simulating many, many different candidate battery materials, and you could do so in minutes as opposed to what is essentially required today, which is that you actually synthesize the material and check it out, measure it.
And so have you come upon the system? I mean, has the system spat out, here's the new material that is most promising?
So for applications that are specific to really, like trying to give a good quantitative description of a realistic material, those are calculations that are going to be more complicated, that are probably going to require an error-corrected quantum computer. So today, what we do is we sort of refine algorithms for solving that problem, figure out exactly how many resources would be required, and just sort of work on compiling it. But we're not putting that on, at least we're not putting classically intractable instances of that problem on the quantum computers we have in the lab today.
Yeah.
But if you go back to the little chart you had here, one of your examples is about, I think, lossless transmission lines.
Yeah.
And what I think you're really talking about there is simulating superconductivity.
Yep.
Now, it's also interesting to do quantitative exact descriptions of specific materials to understand their superconducting properties, but that's a good example of something where often you are interested in just understanding sort of qualitatively what is this phase of matter, what's the mechanism behind the superconductivity in the first place, what's going on. And so in situations like that, you don't need to do this really super realistic simulation. You can simulate what are called condensed matter physics models, which are a little bit more coarse-grained representations of the physics. And those are models that can actually fit on the quantum computers that we have in the lab today.
I mean, how many qubits are you typically running with?
I
know that's a somewhat thorny question because it depends on how you're setting it up. But
so I'm trying to think what the largest chips we've published experiments on are.
Oh, you should
we've
feel free
published
to
experiments on the order of 70 qubits.
All friends. How many?
70 physical
70
qubits. Although we have devices that are larger, but I can only really talk about what we've published about. So,
Right.
But in any event, that's large enough that there are calculations that we can run on those devices that are beyond the capabilities, as far as we know, of any existing supercomputers. And there are some benchmark problems we've run that have demonstrated that. And we haven't actually demonstrated quantum simulations in the classically intractable regime, but we have done quite a lot of quantum simulations that are approaching that point. And my prediction is that you will see results from our team and also from other teams in the next year or two, which are demonstrating classically intractable quantum simulations. So that could include simulations of models relevant for superconductivity or these sort of qualitative models of physics.
And do you have like subsidiary industries standing at the ready to implement whatever it is that these systems?
A little bit. I mentioned for the batteries project that we had worked with BASF, and that's because we had identified the chemical industry as one of the industries that's most likely to benefit. So we do, for a lot of these different applications, we have partners. You have nuclear fusion up here, and we work very closely.
Yeah, I did want to talk about that, if you can give me a sense of where you stand on that.
Yeah, so we actually work very closely with Sandia National Labs, which is part of the U.S. Department of Energy, and a group there that's responsible for doing some of the numerical modeling for these experiments at the National Ignition Facility, which have made headlines in recent years for doing these first inertial confinement fusion reaction experiments where sort of more energy went into the fuel, or sorry, less energy went into the fuel than came out as a result of fusion.
And it all depends how you compare what went in, but that's a separate conversation.
That's right. But it's an exciting sort of milestone nonetheless. And there we sort of learned that one of the greatest challenges in modeling how fusion's occurring, which is very important if you want to optimize the conditions such that fusion's occurring with the highest yield so that your fusion reactor is actually viable, you really have to be able to model it in order to optimize it. And one of the largest sources of uncertainty in their numerical modeling has to do with computing what is called the stopping power. So there are these alpha particles, charged particles, they're generated from fusion and they fly out into this plasma. The plasma exerts a drag, a force of friction on the alpha particle that slows it down, that does work on the plasma, it heats up the plasma, then more fusion occurs, et cetera. It turns out that calculating that force of friction is extremely difficult classically. It's something that the Department of Energy already spends hundreds of millions of CPU hours on a year, and they're using levels of theory which are insufficient. They're very approximate and they're not giving accurate answers, but it's all they can do. But we know, because we did a project on it and worked with Sandia National Labs on this, that we could put those stopping power calculations on a quantum computer. We could get much more accurate answers, and we could do it extremely quickly. That could then allow them to more efficiently model those fusion reactions and optimize the conditions under which fusion occurs.
And so is that now aspirational, or is this being put into practice?
So with the exception of, it's basically sort of all aspirational with the exception of these sort of condensed matter, more qualitative simulations I mentioned before. So really, we think about quantum computing in two eras. There's the era that we're in today, which is often called NIST, or Noisy Intermediate Scale Quantum. It's playing around with the devices we have in the lab. There are things we can do that are classically intractable, but because of noise and decoherence, we're limited to on the order of 1,000 to maybe 10,000 operations. And then there's the era where we're able to implement algorithms within fault tolerance. And there we can implement much more elaborate algorithms that have millions or billions of quantum gates. That's where realistic simulations of, if you want to, so in the stopping power calculation, you really want to know what is this force of friction to, within say 1% error or something. So you really have to model the specific material in detail. It's a bit different than, I want to know if there's, what is the broad mechanism that is creating superconductivity in this condensed matter model. And so things in that second category are sort of in scope for NIST, but things that are really aiming for realistic quantitative descriptions, those you'll probably need fault tolerance.
And this other application that we saw up there in terms of catalysts, and is that another promising area? Is that one also that's
Yeah,
in the work?
definitely. So this really has to do with simulating chemical reactions. So a catalyst is, it's a molecule that you add to a chemical reaction that lowers the energy barriers involved such that the chemical reaction could occur with less energy. And it turns out that many catalysts, they involve metals, which means that there's a lot of electrons involved and they're very difficult to simulate on classical computers. So a good example of an interesting catalyst application is, I think you said something about fertilizer production up there.
Yep.
So the way that humans have made fertilizer since about World War I uses something called the Haber-Bosch process, which takes a tremendous amount of energy. You take hydrogen gas and nitrogen gas and you heat it together 500 degrees Celsius and megapascal pressures, and that creates fertilizer. You have to break the triple bond in nitrogen, which is it's a very stable compound, so that's a difficult thing to do. However, we also know that there's this bacteria that lives on the soil of bean plants, and this bacteria, it has an enzyme called nitrogenase, and this enzyme nitrogenase, it has a catalyst in it, which is called FeMoco. It's the FeMo, or iron and molybdenum cofactor of nitrogenase. Anyways, this thing is responsible for just sort of magically breaking that triple bond in nitrogen, and it allows this bacteria to create fertilizer at ambient pressure and ambient temperature, just regular conditions like what we're experiencing in this room. That's to be contrasted with the Haber-Bosch process, which consumes about 2% of the world's energy. So if you could, it turns out that simulating that physics, simulating how FeMoco is breaking that triple bond is sort of a famous open problem in chemistry. It's something that classical computers cannot do or haven't been able to do efficiently, but we know how to put it on a quantum computer. The hope is that if you could simulate this FeMoco molecule, you could understand the mechanism by which nature is doing this and maybe introduce an industrially viable form of this catalyst that could be used to make fertilizer at scale with dramatically less energy and save 2% of the world's energy.
Which should be amazing.
That would be amazing.
Yeah. And so as you look to the future, obviously there's the arena of the hardware, which is very difficult, but it seems that you're heading in the direction of being able to have these systems stay coherent for longer, having larger number of qubits and so forth. Do you think that developing the algorithms to run on these systems is going to itself at some point be a bottleneck? I mean,
absolutely. So if you take the example of simulating FeMoco, that's actually been a benchmark in the field of quantum computing for some time now. And we've known for a long time, for 20 years, that in principle, you can efficiently simulate chemical reactions on a quantum computer. But when I say efficiently, I'm using the word as a computer scientist uses it, which means that in polynomial time, you can simulate it. But what is the actual...
polynomial in the number of...
In the number of electrons, we'll say.
Okay.
Yeah, whereas a classical computer necessarily scales exponential.
Right.
So, in principle, it's better, but if you actually want to simulate a system like FeMoco, you really care what is the order of that scaling. Is it scaling like the number of electrons to the 10th power or to the 3rd power? And when people first started, sort of pricing out what will be required, they became very discouraged. The first real serious paper to look at this was in 2013 by Microsoft, and they found that the best algorithms they knew of at the time would take n to the 10 operations, and to simulate FeMoco, 10 to the 20 operations would be required, which is, even on a quantum computer, which is exorbitant, right?
Yep.
But in the last 10 years, since then, that was sort of the starting gun for algorithmists like myself to start thinking about these problems and improving the algorithms. For solving that problem, the algorithms now improved to about n to the 3, and the number of operations is about 1 billion, so 11 orders of magnitude improvement. So this transitioned a quantum computer from solving that problem in millennia to solving it in a matter of minutes.
And what does it take, do you think, as someone who actually does this, to be able to make progress in this? I mean, do you need to understand the quantum mechanics of Schrodinger's equation really well to sort of see some structure in there that you can leverage and make the simulation work better? Or is it just thinking in terms of, algorithms and just how to speed up, whatever, n to the 10th to n to what would it take to do that?
So I think that algorithms research, it's sort of easy to think about it in two kind of separate categories. One category is developing fundamentally new quantum algorithms for a new problem where we didn't know there was a large quantum speedup. And there, I think it has a lot to do with sort of reasoning about the structure of that problem, and also thinking about quantum mechanics and what it has to offer as a computational resource. When it comes to doing the sort of work that is, reducing the scaling of a quantum algorithm, it's a little bit more similar to the traditional computer science study of algorithms, and it's work a little more similar to thinking about compilers and. But also very important to sort of both sides of this is having a fair bit of knowledge about the domain that you're applying it to. A lot of those advances in simulating quantum algorithms for chemistry have come from essentially insights that have come from quantum chemists. Like, well, there is this structure in the molecular system that you could exploit to sort of in your quantum algorithm. So it's very helpful to have knowledge of both the quantum algorithm side and the domain application side.
And so if you then sort of move away from these very specific quantum mechanical applications, and you start thinking about AI, machine learning, where do you come in there? What's the role of all this breakthrough?
Yeah, well, being at Google, AI is definitely a thing that we think about. And on the face of it, you might be very encouraged by, at a very high level, what quantum computers promise, because we know that quantum computers, they're sort of a superset of they can compute functions efficiently that are sort of a superset of the functions you can efficiently compute on a classical computer. And most of machine learning, it's about basically computing some probability distributions to model some data that's provided. We can always interpret the quantum state as a probability distribution, and we know that we can prepare very complicated quantum states on our quantum computers. And so we know that there are many probability distributions we can efficiently represent using our quantum computers that you cannot represent using classical computers. So you might think, oh, maybe I'll just sort of parameterize these quantum circuits with some free parameters, the way that you sort of parameterize a neural network, and then you can kind of tweak those parameters to reproduce some probability distributions corresponding to data. And that's kind of a nice idea, but there's a lot of questions that come up immediately, like, well, okay, yes, in principle you can represent many more probability distributions, but can you efficiently find the right parameters? Or what are the data sets that are really going to benefit from this in practice? And theoretically, we are able to prove some things. We are able to show some data sets. Often they're of a little bit of a contrived nature where we can get a quantum advantage that's decisive. But the sort of difficult thing about this area is that historically, machine learning is not an area that advances through theory, through pencil and paper. It's something that is advanced through just sort of trying things out and seeing what works. It's sort of, most of machine learning is sort of honed empirically. People have some idea for how they're going to realize a neural network, and they start tweaking little aspects of it and seeing how they can make it work better and what works and what doesn't. And the difficult part of this for quantum machine learning is we have only relatively small quantum computers today. And furthermore, we can't efficiently simulate larger quantum computers. So it's a little bit speculative to say, how well are these going to work for modeling very large data sets, for example.
Right. But presumably there's some degree of optimism that you will make a difference, maybe even a significant difference.
I think that there's some problems in machine learning where we can be relatively certain quantum computers will make a big difference.
So I just want to, I don't mean to interrupt, but I'm just wondering, so does it give you any pause that we're going to be in a likely situation where, a handful of these major corporations are the only ones who really have the power to implement and create these systems? Now, I mean, I'm not asking you to, well, I guess I am asking you to, be frank. Does it concern you?
Well, I think this is a little bit of a non-answer, but I think that it's a little bit analogous to the situation with the capability to, train large language models or something like this.
Yes.
But I think quantum computing as sort of, similar to GPU clusters or something, and that they're a resource for high performance computing. That, the interest of Google ultimately is being a provider of quantum computing resources. Our sort of end game is to have a business where people log on to Google Cloud and they are able to run their workloads using our quantum computers, and we provide that as a service. And so, our interest is ultimately in, sort of helping to uncover these applications so that we can drive, external users to have a need to use our platforms, and we hope to produce enough to meet that demand.
And so a long time ago, there's this famous story, I forget which company or which individual is implicated in this, that there was this notion of classical computers, which is all there was at that time. They're so specialized that there are going to be a few of them in the world for just a few individuals. There'll never be, the kinds of devices that we walk around with. What will it be with quantum computing? Is that older vision maybe the correct vision for quantum computing, or is that again just being lack of imagination for where this is going?
So I do tend to think that quantum computers, at least the first few generations of commercially useful quantum computers, will be somewhat specialized instruments for problems that really require, special types of problems that admit a large quantum speed up. And many of those problems are going to be of a scientific nature. But I also think that, as you say, we shouldn't be sort of myopic about, it's sort of easy to, not see where the technology is really headed in the long term. Nobody saw, the internet coming in its current manifestation. And, McKinsey wrote these hilarious documents in the late 90s about how nobody's going to use cell phones. And I think your quote was from the president of IBM, who in the 50s said he foresaw a need for at most five computers in the world. Right? So I think that there's definitely some of that going on. I don't think that there's any reason you're going to be composing emails on a quantum computer. I don't foresee it being in your phone or anything like this. But one application of quantum computing that I am rather bullish about is using quantum computers to build better quantum computers, because a lot of the things that are limiting our ability to make quantum computers right now are essentially material science problems of a very quantum origin. For example, in superconducting qubits, the thing limiting the coherence time of our qubits is that there's mysterious defects that move around on our chips, and we don't know what they are. And it's the sort of, is it paramagnetic oxygen molecules, or is it, some kind of water or something? And in principle, if we could do certain quantum simulations, we could help figure that out and maybe remove these impurities. And there's some very exotic architectures of quantum computing, like what Microsoft is committed to building, a topological quantum computer using Majoranas, that I think it's quite possible that may be the end game for the technology, but that you may need a superconducting qubit quantum computer in order to simulate the physics of these sort of topological materials, and to figure out how to build those devices in the long run. And once you're using quantum computers to build better quantum computers, there's a feedback loop here where you could really imagine the technology going in surprising places.
Surprising, scary, hugely exciting. So let's stand on the sidelines from my perspective and wait for you and your colleagues to show us what's possible. So thank you so much.
Thank you.
Thank you.